Hello again, physics friends. Today we are going to learn about a tool that helps us understand relativity in a graphical way. Again, this is not a new effect, right? We've already covered all of the main effects of relativity: rear clock ahead, time dilation, length contraction. But the use of these so-called space-time diagrams helps us think about problems. So it's another tool that we can make use of in our toolkit. We're going to start out with a kind of simple setup that has nothing to do with relativity, but we're just going to use it as a way to make sure that we understand that we can plot the position versus time of objects in a diagram. Okay, so for example, let's bring in this picture here, which is an image of a clock that's at rest in a ground frame, and a tree that's also at rest on that frame, and then we have a truck that's driving to the right at 1 meter per second. Well, if it's driving by to the right at 1 meter per second, then let's say 1 second later, we have the same situation as before. Clock hasn't moved, tree hasn't moved, clock has advanced from 0 to 1, but the truck has moved. It's moved 1 unit over to the right, 1 meter over to the right in 1 second of elapsed time. So what would this look like if we were to make a picture, a diagram of the position of the tree and the position of the truck as a function of time? So that's our next task, is to make that picture. So here I've laid out a set of axes in which I have a time axis and a space axis. So you may be more familiar with plots where we make a graph of position as a function of time. And here we're making a plot where time is a vertical axis and position is a horizontal axis. And the goal, or the reason for that in part, is because we can think of the actual snapshot itself as having an x-coordinate, and that is going to be parallel to our graph axis for space. Okay, well, let's start with a tree, okay? And I'll use purple for the tree's location. I'll color the tree purple for some reason. Okay, so we know that the tree starts at an x-coordinate of 0 at time 0, and the tree is always going to be, the tree's at position of 3 at time 0, and the tree's always going to be at a position of 3 for all time in this ground frame. So let's make sure we label that properly. This is x in the ground frame. Okay, so we know that the tree starts at x equals 3. 1 second later, it's at x equals 3. 2 seconds later, it's at x equals 3, and it's always at x equals 3. So we can actually just draw the position as a line, because the tree is always at 3 for all time, not just 1, 2, and 3 seconds. And what we're going to call this is the tree's world line. Okay, and we'll use that term world line to represent a trajectory through space and time. Now, the tree's trajectory is rather boring. It's just a vertical line because it's not moving. It has a constant position for all time. The truck has a world line that's a little more exciting, right? So what color can we give the truck? How about, why don't we make it blue? Okay, so we have this blue truck, and it starts with a position of 6 meters at time 0. And 1 second later, it's at 7 meters. And at time equals 2 seconds, now the truck is at 8 meters, and it's just going to continue to move 1 meter to the right for every 1 second of elapsed time. So the world line of the truck looks like this. And notice that the truck in this frame is not at rest, and so its world line is tilted or slanted. And the slope of the world line tells us something about the speed, right? So let's look at this a little bit. The slope of the world line is a change in time, that's like the rise, over the run, delta x. So if you like, that's rise over run. Okay, and for the truck, the rise is 1 second for a run of 1 meter. And so the slope, it's not the velocity or the speed rather, but it's the inverse of the speed. So we have slope equals 1 over the speed, or the speed is 1 over the slope. Okay. Well, for the tree, the velocity is 0, so the slope is 1 over 0, or infinite, and indeed, this purple line has an infinite slope. It's a vertical line, okay? The one thing I want to point out here is the following before we move on. We have an object at rest in this example. It's a tree. And notice how the world line of the tree is parallel to the time axis. So I'll use these little symbols, 2 arrows on 2 lines. I'll use that to indicate that those are parallel to each other. So what we can say is a world line of an object at rest is parallel to the time axis. Okay, and that's simply shown here, that the purple line is parallel to the black time axis, and that's because the position of the object is constant. Okay, so this example is likely quite straightforward, and maybe perhaps is even something you've seen before. We're going to complicate this a little bit in the next example. We'll go to, we'll actually return to this relativity of simultaneity example that we did early in the course, where we had Alice on a train and a light source emitting 2 photons from the middle of the train, and those photons are traveling to the 2 walls. This time we're going to make a space-time diagram of that setup. And we're going to do that in 2 frames. We're going to do it in the train frame, and we'll do it in the ground frame. And we'll see how they're similar and how they're different. And what we're going to find, is that we'll be able to determine things like whether events are simultaneous or not, just graphically, with no calculations and no equations, just simply by looking at the graph. So let's get started on that. Okay, so we're going to work with this example that we've seen before, where we have a train, and on it, right in the middle of the train, is a light source that shoots out 1 photon in each direction. And those photons come out simultaneously. We're going to be doing our analysis in the train frame. And just first, to give specific numbers, let's say that the full train is 20 feet wide, so that the light source is 10 feet from either wall. In the past, we've just kind of drawn and labeled the diagram in this way, but I think for this example, it will be helpful to think of an underlying number line here that represents the x-coordinate, and we'll put the light source at the origin, x equals 0, which puts the 2 walls at plus and minus 10 feet relative to that origin. Sometime later, those photons will arrive at their walls. And in particular, we know that in this frame, the photon arrives simultaneously because they're both traveling at the speed of light, and they both have to travel the same distance of 10 feet. Okay? We're going to define 2 events and name them. We'll call EL the event left photon arrives at left wall, and we'll call ER right photon arrives at right wall. And what we can say is in this frame, EL and ER are simultaneous. Okay? So what our hope is that we'll be able to draw a diagram, a space-time diagram for these events, and show graphically what it means for them to be simultaneous. One final piece of information that we'll need is what is the elapsed time in the train frame for in between these 2 events, right? So if we say that the launch of the photons happens at t equals 0, what is the reading on a clock at rest on the train when the photons arrive? Well, that's pretty straightforward, right? We know that the photons need to travel 10 feet. They're moving at 1 foot per nanosecond. So when the photons arrive, this clock reads 10 nanoseconds. In other words, the elapsed time is 10 nanoseconds for these events to happen between the launch event and the arrival event. So each photon takes 10 nanoseconds to reach the wall. Okay, well, we should now be able to draw a diagram indicating the time of launch, the time of arrival, and from the diagram, we should be able to see that the events are simultaneous. So here I've drawn a set of axes, and I might just indicate one thing, which is that the lamp that releases the photons and does so at t equals 0 does not move in this frame. So I'm going to draw in purple the world line, or the trajectory in space-time of the lamp. And the lamp is at rest. So it has a vertical world line. Well, how about the world line of each photon, right? Well, let's look at the rightward photon first. We know that it starts at x equals 0 at time 0, and it ends up at x equals 10 at time equals 10. So if we draw that out, we'd expect to see that that photon reaches x equals 10 at a time of 10. So this red line is the photon world line, and I guess at this point it hits the wall and then gets absorbed by the wall. In addition to drawing the lamp's world line, let me also draw the world line for the right wall. The right wall starts at x equals plus 10 and it stays there forever. So here I can draw a vertical line at x equals 10, and this is the right wall's world line. Okay. And similarly, we can draw the left wall's world line. Okay. So everything attached to the train has a boring straight up world line. And the photons, however, move up and to the right for the right going photon, and then what we'll see next is up and to the left for the left going photon. The left going photon starts at x equals 0 at time equals 0, and then it ends up at x equals minus 10 nanoseconds later. So we can draw that. It's going to end up at this point, x equals minus 10 at time equals plus 10. So its world line connects these two dots. And if you'd like, we can eliminate the world line once the photon hits the wall, because we can then say the photon has just been absorbed and there's no more photon. Now that we've drawn a space-time diagram for the situation, let's talk through some of its features. So here we have the same space-time diagram as in the previous slide, and we're going to use this to talk through some of the features of this that we see. Okay, so one thing that we notice is that world lines of objects that are at rest are parallel to the time axis. So those are lines of constant position. So we have three objects, right, that are at rest. We have the wall, the two walls rather, and we have the lamp, and those world lines are straight up and down. So we can draw a vertical line as a line of constant position, right? Every single point on this line has the same x coordinate. It's a line of constant position. So a vertical line is a line of constant position. The other thing that we notice is that we know that we have two events here. The first event that's happening at 10 nanoseconds is that the left photon hits the left wall. And the second event that we have also at that same instant of time, simultaneous, is the right photon hits the right wall. So we have the fact that these two events, let's call them E left and E right for the left event and the right event, those are simultaneous. Okay. So because they're simultaneous, we can then define a line that goes through those 2 points. And that line we can call a line of simultaneity. Okay, so let's see. Let's pick maybe blue for our line of simultaneity. And we notice that a line of simultaneity is parallel to the space axis. It's a line of constant time. What that means is any point on this blue line has the same time coordinate, 10 nanoseconds. So we have horizontal, not always horizontal, but in general, that line will be parallel to the space axis. Okay, so I'm going to indicate, remember how I indicated parallel using my little arrow symbols? Okay, so my line of simultaneity, the blue line, is parallel to the space axis. And my line of constant position is parallel to the time axis. Okay. Good. Another thing that we can notice is that these events, E left and E right, they are points in a space-time diagram. So they have no volume or extent, but they are points. So we could say that the event E left is a point that has coordinates T left and X left. And let's do X comma T. So it has a coordinate X left and T left, where X left is the X coordinate of the event and T left is the time coordinate of the event. In this case, the X coordinate of the event is minus 10 feet and the time coordinate is 10 nanoseconds. E right also has an X and T coordinate. Here the X coordinate of the right event is 10, but the right coordinate, the time coordinate is the same as for the left. So it's plus 10 feet in X and 10 nanoseconds in time. And because these two events have the same time coordinate, that means they are simultaneous. So we can say the events are simultaneous when T left equals T right. In other words, events that share the same time coordinate are simultaneous. Okay. One more feature that I'd like to point out is that we have these photon world lines. So let me label those. So this is a photon world line. Okay, and that's for the right photon. And I also have a photon world line for the left photon. Okay. And notice something about those photon world lines, right? A photon travels 10 feet in 10 nanoseconds. So this world line is midway between the space and time axes. So we can say that in general, a photon world line bisects the space and time axes. Okay, so what does that mean? Well, if I have my space and time axes, my photon world line is bisecting that axis. That means the angles between the time axis and my world line is equal to the angle between my space axis and the world line. Okay, why don't I just say 45 degrees? Well, in general, we're going to see it's not always going to be 45 degrees because what we're going to see in the future is that if you draw another frame of reference, say the ground frame, those axes might be compressed relative to the original set of axes. And it's not the case that the photon world line is 45 degrees away from either axis, but it is the case, and always will be the case, that the photon world line is midway between those two axes. Okay? So let's call this angle theta. Those two angles are the same, but in general different than these two angles. Although these two angles are equal to each other, and these two angles are equal to each other, theta and phi, those angles are not necessarily the same, and they're only 45 degrees in one frame of reference, but not in another. So instead of saying that, the term that we'll use is that photon world lines bisect the space and time axis. Okay, good. So we have a set of features for the space-time diagram. Next, I want to look at exactly the same situation. Okay, two photons launch from the middle of the train, but this time we're going to view the situation from the ground frame in which the train is moving. Let's see what that looks like. Okay, so here's the same situation shown in the ground frame. And again, the launch of the photons is simultaneous, so they're both happening at this one in this one snapshot diagram. We see that the train walls and the lamp itself are moving to the right. And let's give them a specific velocity of 3/5 c. And I should draw the lamp also in the second diagram. The photons are moving at the speed of light, as they were in the other diagram. And I've drawn in the second snapshot diagram the instant that the left photon hits the left wall, which happens before the right photon hit the right wall because the left wall is approaching. Okay, so we'd like to capture this situation using our space-time diagram. So what I want to do next is actually draw the space-time diagram, axes in the ground frame, and then we'll start by drawing the world lines of the train walls. First, let's just establish what the size of the train is. In the frame in which the train is moving, so we're in the ground frame, the train is moving at 3/5 c. If we lay down a number line that's in the ground frame, okay, and let's make the center of the train in the very first snapshot diagram, let's say that center is at position 0, then what is the coordinate of the left and right edge? In the train's ground frame, the train was 20 feet long, so the two coordinates were minus 10 feet and plus 10 feet. But we have a moving train, and the moving train has a speed of 3/5 c, which corresponds to a gamma factor of 5/4. So the length of the train L is equal to its rest length contracted by this factor of gamma, and the total rest length of the train is 20 feet. We divide that by 5/4. 20 over 5 is 4. 4 times 4 is 16. So we have a total train length of 16 feet for the moving train. So that allows us then to identify the coordinates of the ends of the train. So if a total length is 16 feet and the middle is at 0, then the ends are at plus and minus 8 feet. So when we come to our space-time diagram, we're going to put the train initially, the train walls rather, initially at plus minus 8 feet, and at 0, well, that's where the lamp starts. If the train were at rest, its walls would have world lines that were straight up and down, but the train is moving in the ground frame, right? So as time goes on, the position gets further to the right. So instead of having a vertical world line, we'll have world lines that are tilted. And the amount of tilt, the slope of those world lines, depends on the velocity. Remember, the slope is inversely proportional to the velocity. So let's write this out. The wall has a world line with a slope given by rise over run. The rise is a change in time over a change in position, okay? And we know that for every 5 nanoseconds of time, the train travels 3 feet. In other words, the speed of the train is 3 feet per 5 nanoseconds, or 3/5 c. So we're going to have a slope of 5 over 3. So let's start with the lamp, okay? The lamp is going to it starts at 0, 0, and it's got a slope of a rise of 5 and a run of 3. So it's going to look something like this. Okay. And so this is the lamp, the world line of the lamp. And the world line of the right wall will be parallel to that. World line of right wall. And the world line of the left wall will be parallel as well, because it has the same speed. So we can label that world line of left wall. Well, next we can draw the world line of the photons. And remember that the photons' world line bisect the space and time axes. Okay, so the left-going photon is going to emerge with a world line such that these angles are the same. This world line bisects the axes, and out it goes. When the photon's world line intersects with the world line of the left wall, that is the event EL. Left photon arrives at left wall. That's that red dot that I placed down. Now, the right photon is also going to emerge in such a way that it bisects the space and time axes too. Okay? So here we have the time axis, the space axis, out comes the world line, such that those two angles between the space and time axes are equal. So we're going to draw this line, and extend it out. And right away we can see very clearly graphically with no calculations, okay, that the right photon is going to hit the right wall at a later time than the left photon is going to hit the left wall. Okay, and we can show that just graphically. So let's do that here. The time coordinate for EL is this coordinate, TL, that time. The time coordinate for ER, well, that is given by this point, TR. And we can very clearly see that TR is bigger than TL, which means that ER happens later, or happens after EL. So these events, E left and E right, they were simultaneous in the train frame, but they are not simultaneous in the ground frame. Okay, so EL and ER are not simultaneous in this ground frame. I also really appreciate one aspect of these space-time diagrams, which is that it becomes very clear graphically why the left photon arrives first, right? You can see that the left photon hits the left wall before the right photon hits the right wall because the left wall's world line is angled towards the photon, meaning the left wall is approaching the photon, whereas the right wall's world line is angled away from the photon because the right wall's is running away from the photon. So it's very clear graphically that these two events cannot be simultaneous in the ground frame. Incidentally, you might be wondering, okay, well, they're not simultaneous, but can I actually, from the diagram alone, calculate TL and TR without using any equations? If you're wondering, is that true? The answer is yes, absolutely. As long as you draw this diagram carefully, using grid paper or draw it accurately in a way where you can read numbers off of your graph. So let's play that game on the next slide. Okay, so I have drawn on a much larger scale the space-time diagram in the ground frame showing the motion of the train walls and the motion of the photons. And what we can see here is, just as an example, let's take the left wall, which starts at -8 feet at time equals 0, and it advances 1, 2, 3, 4, 5 nanoseconds and 1, 2, 3 feet. So this wall moves 3 feet to the right for every 5 nanoseconds of time. So we have a slope of 5/3. And again, 1, 2, 3, 4, 5. 1, 2, 3, and we put another purple dot there, and we repeat that process all the way along. 1, 2, 3, 4, 5. 1, 2, 3. We put another dot there. So we know exactly how to draw the world line of the left wall. Then we can look at the photon's world line. The left-going photon starts at the origin, and it goes up 1 unit of time for every 1 unit of space. Up a unit of time, over a unit of space. Up a unit of time, over a unit of space. So its world line is just going to connect all of the intersections of these grid lines. And so I can do this and draw this out. And what I can see is, from this graph, I can just straight up read off the position of the intersection. So it would be x equals -1, -2, -3, -4, -5 feet. That's where the wall will be when the photon hits it. And the time that the time in the ground frame when this will occur is at t equals 0, 1, 2, 3, 4, 5. Okay, so we see TL equals 5 feet. All right, and let's just make sure that that's a sensible answer. So if I take, I'm going to kind of create myself a little work area over here. Okay. If I wanted to calculate the time delta t ground for the photon to hit the wall, I can do it quickly by looking at the initial gap size and divide it by the gap closing speed, or the gap closing rate. Well, the initial gap size is the distance between the photon and the wall at the start of this journey, and that is 8 feet. The gap closing rate has two contributors. One is the speed of light because the photon's moving, and the other comes from the fact that the wall is moving at 3/5 c. So this gap closing rate is c plus 3/5 c because the wall and the photon are moving in such a way as to close this gap. Well, c plus 3/5 c is 8/5 c, and c is 1 foot per nanosecond. So when I multiply this out, I get this cancellation of the 8, and I'm left with 5 nanoseconds. So indeed, we predict that delta T ground for the left photon to make its journey is 5 nanoseconds, but that's exactly what we read off of the graph using no equations and no calculations. Well, let's do a prediction then for the right wall, delta T ground for the right photon. Okay, and again, that's gap size over gap closing rate. Once again, the initial gap size is 8 feet, right? The photon starts at the origin, and the wall starts at 8 feet away. And we're going to divide that by the gap closing rate. Now, we have two contributors once again. The photon is closing the gap, but now the wall is increasing the gap. So instead of adding c plus v, we subtract the two because the wall is increasing the gap. So it is a negative gap closing rate. Well, when we do this out, we have 8 feet over 5/5 c minus 3/5 c is 2/5 feet per nanosecond. Our units of feet cancel as before, but now we have, instead of 5 nanoseconds, we have 8 over 2, which is 4, and 4 times 5 is 20. So we have 20 nanoseconds. So we predict that if the photon was launched at t equals 0, it will not arrive until t equals 20. Okay, well, from the diagram, right, we've drawn this photon world line so that it goes through every intersection of our grid, right, because it goes over a foot and up a nanosecond, over a foot and up a nanosecond. And the wall, we've gone over 3 feet and up 5 nanoseconds because its speed is 3/5 c. 1, 2, 3 feet, 1, 2, 3, 4, 5 nanoseconds. And you can see I have these little dots every 3, 5, 3 units to the right, 5 units up. I put a dot down. And notice this dot up here at the very top right is exactly where the photon hits the wall. And if we read that point, if we read off the time associated with that point, okay, that will come over to our time axis here, and we'll call that, let me make a little space for us in here to annotate the diagram. We'll call this one TR, and then we just count boxes, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Lo and behold, it is indeed 20 nanoseconds. So we can use our space-time diagrams quantitatively in the same way that we can use our equations. So these space-time diagrams are just another tool for understanding and calculating quantities in special relativity. So I hope you've enjoyed this kind of foray into space-time diagrams. Now, the key here, though, is that we'd like to be able to represent both frames of reference, not just one, but both frames of reference in a single diagram. So that's what this next video will be talking about. How do we make a space-time diagram that represents both the train frame and the ground frame? So our next video will show you about that. Until then, be well and take care.